Okay. So there's this question.
How get this? Okay.
How wet and warm if you haven't signed, it's a final exam bonus. I don't have it. It's a stylus.
Oh.
Okay, so ocean on Mars, early or not. And again, this really comes back to the issue of, was Mars warm and wet early? Was it cool and damp? Was it cold and dry? What really can we infer about the past climate and hydrology of Mars? Okay. Clearly there's no ocean on Mars today, right? We've seen that. This is a view of Endeavour Crater, which is Opportunity's most recent stomping grounds. And what do you see? What do you see?
A bunch of dirt.
Bunch of dirt. Actually, as far as we know, there's no dirt on Mars because dirt implies inorganic matrix and living stuff. So soil that you all take for granted is really a complex thing. We see regolith, which is broken up rocky material. We see larger rocks. We see dust. We see not a lot of water. Okay, Mars today looks very arid, and it really is. Here are just some pictures from Gusev Crater. So before Spirit ceased operations, it was in this crater that clearly had been filled in with lava at some point. It eventually climbed up into the Columbia Hills, up Husband Hill there. But still, you look out, it's a very arid landscape that we're looking out on. So the question is, was there an ocean on Mars in the past, and which was lost over time? So clearly we don't have a time machine for going back to answer that question. So to answer the question, what do we need to look for? What kinds of data do we need to collect? What kinds of evidence do we need to analyze to address the question of whether or not we can say there was an ocean on Mars in the past? Ian?
More intense weathering in certain locations.
Okay. So you're thinking that the water in the ocean would leave a signature in terms of how it weathered the surrounding areas. If there was water in the ocean, presumably it would have led to erosion, and that would have left its mark on the area surrounding, on the ocean basin. Wherever the water is in contact with the ocean basin, that water could presumably weather and erode rocks in ways that you wouldn't expect if there hadn't been water there. That's probably the primary thing we can look for, but are there some other things we might look for? Yep.
Minerals that wouldn't exist without ocean.
Minerals formed in the presence of water. Do you have any idea about what the bottom of our ocean is like now? I mean, none of us have necessarily been down there. Go ahead.
Is it like really high pressure?
Okay, there's currently high pressure. Obviously, that high pressure would go away when the water went away. Would the high pressure itself leave any kind of mark?
Sedimentary rocks.
Possibly not, but we in general will see sediments accumulate at the bottom of an ocean basin, which could turn into rocks. Yeah.
I don't know, but couldn't the rocks that they may find under the ocean maybe like smooth because of like constant water movements? I think the rocks are this
Smooth rocks. So sedimentary layers, generally speaking, if you look at the bottom of large lakes and oceans, they tend to be fairly flat. Flatter than just regular terrain. I moved out here from Fargo, North Dakota, Moorhead, Minnesota area, and that whole area is the bottom of a glacial lake called Lake Agassiz. You know, glaciers had dammed up the rivers, built up this huge lake in the area. It's some of the flattest farmland around, and all very much fine-grained soil because of all of the sediments that had been washed out and accumulated in Lake Agassiz that then just kind of rained down to the bottom of the basin, forming this flat, finely layered, fine sediment soil that was left when the glaciers receded and the lake went away. So the point is, you know, something as large as an ocean on Mars would leave a big impact on the terrain, and the question would be, you know, can we 3.5, 4 billion years later still see evidence of that or not? Here's another example of glacial lake systems in the western United States. In particular, this Lake Bonneville area has been extensively studied. We've mentioned this before in class. This is where we see all of these salt flats where they do the land speed velocity record attempts with the souped up rocket cars trying to go just that much faster without crashing and killing themselves. So what kinds of structures do we see? Well, the flat, salty lake bottom sediments are one clue, but what I want to point to in particular, you see this kind of line that goes across the hillside here. It's a relatively flat line. If you weren't looking very closely and you thought it was off in the distance, you might expect that to be perhaps a road cut or something. This is actually a terrace that represents the past lake level for Lake Bonneville, where the surface waters would have eroded the areas matching up with the top of the lake as those waves constantly being blown across the lake hit the surrounding hillside, rode away a little bit of the erosion, and it's very flat because, of course, the surface of the lake, by definition, has to be flat because gravity is going to pull the water down to a constant level. Okay. So this is what it looks like, on the ground, looking, say, at an ancient shoreline here on the hillside. Also, we can also see these structures in aerial photographs. So, it's probably not real clear in the unlabeled aerial photograph, but if you look, there's this line that runs across across this area where Lake Bonneville used to have a shoreline. And it's a little bit clearer here where someone has drawn a nice little line across here. So at one point, this glacial lake, which is not here anymore, lapped up against the shore in this area and left this shoreline. And then above that shoreline, there are these various deposits of material that are oftentimes laid down in the kinds of dune areas that surround some of these ancient lakes. But what's most striking here is this shoreline. So the question then becomes, if there was an ocean on Mars and it's lasted for any length of time at all, we could look for these kinds of paleo shorelines, paleo meaning old, kind of fossil shorelines, to see if we can identify similar structures on Mars. Okay, so this is not aerial photography, but orbital imagery from Mars. And these are some of the areas that were identified originally on the basis of Viking images, but later examined in more detail with cameras on the Mars Global Surveyor, the MOC instrument, the Mars Orbiter Camera. And you can see that just as there was in the aerial photograph for Lake Bonneville, you see the same kinds of things of, in this case, successive shorelines that could represent different lake levels, different ocean levels of this ocean as the ocean gradually dried up and then stabilized for a little while. It would have been there for long enough to erode a shoreline, and then another episode of ocean loss took place. The ocean level would drop again and then stabilize and cut a new shoreline. So that's the proposal. That's the hypothesis that's was proposed about 10 to 15 years ago. Okay. So this isn't as effective as a small diagram like this, but essentially Tim Parker and colleagues, but Parker was the Parker of the Hawaiian shirts question, was the one who really proposed this hypothesis and pushed it, even while he was a graduate student. So that's pretty ballsy to propose this major hypothesis and keep at it in the face of pushback from established researchers. He spent a lot of time looking at images of Mars taken by the Viking orbiters, trying to identify what might be pieces of shoreline, and then trying to follow those fossil shorelines from one image to the other, going through all of the imagery that had been sent back by Viking and then later by Mars Global Surveyor and so forth. And what he proposed were a couple of shorelines, one called Arabia and the other called Deuteronilus. And spent a lot of time just trying to trace them around from one area to the other through these images. Actually, I have a better picture coming up later, so let's go on to that. So here is a picture. Now again, where would we expect the ocean to be on Mars? Northern lowlands surrounding the North Pole of Mars. So this is a view of Mars looking down on the North Pole, and I'm not. This is possibly infrared imagery from the Themis instrument, but basically it shows the The North Polar area, you can see these existing basins that are the lowlands. So Utopia, the North Polar Basin, the Amazonas Planitia lowlands, the Isidis Basin. And, if you plot those two main shorelines around the North Pole, which is right here, you see the Arabia shoreline is a little bit further out from the pole. And here's a little bit more of it. And the Deuteronilus shoreline is a little bit closer toward the pole, and there's some of it here. It goes a fair amount of way around the pole, but then it's broken. There's a little bit more of it identified over here. Do these look like ocean shorelines? Yeah, in what way don't they?
Well, I don't know if this is like intentional, but like there seems to be a lot of like missing spots.
There's shoreline missing. I mean, if you look at the Atlantic Ocean, Pacific Ocean, you don't have shoreline for a while and then no shoreline. So one question is, why aren't these intact? Why don't we see a complete circle, say, for that Deuteronilus shoreline?
Couldn't it just be because of volcanism, like going over the shore?
Okay. So if there were an ocean here, it would have been 3.5 billion years ago. And a lot of crap can happen to a planet in 3.5 billion years. So, the fact that these shorelines are not complete is not a fatal problem with the hypothesis. It just could be that, well, something has happened over here, say, to obscure the shorelines that used to be there. And can you identify any of these landforms? What? There's Olympus Mons here. There's the Tharsis volcanoes, Pavonis Mons, and Arcia. I can never remember which is northern hemisphere, which is the other. And then, I think I mentioned Alba Patera, which is not as tall as Olympus Mons, but in terms of volume, it is one of the biggest volcanoes. So clearly, that whole Tharsis development there could have just obscured the shoreline. This is just showing a different view of it. To some extent, the Arabia shoreline tends to follow more closely the boundary between the southern highlands and the northern lowlands. And the Deuteronilus shoreline, so that's this one out here, again kind of follows that break between highlands and lowlands. And then the Deuteronilus contact is in from that. So which of these contacts would be higher elevation?
Arabia would be
Why?
because closer to the higher stuff.
Okay, yeah, Arabia would be. So if these both were oceans, the Arabia shoreline is wider and higher. Which of these oceans would have contained more water if they were both oceans? Arabia. Okay. So one interpretation would be, well, maybe there was an ocean in the past, and the Arabia shoreline represents, its kind of maximum extent during the early, wetter, warmer days of the Noachian. And that's why we've got that shoreline there. And then things started to get crappy on Mars, and the ocean started to get lost. But something stabilized it long enough for a smaller ocean to carve this this second shoreline. That would be one way to interpret this. Yeah, I don't know if I want to say a lot about this. What we see some structures in these northern regions that are associated with a lot of water. So we see a lot of these rampart craters where it looks like the crater is surrounded by all this slushy material that got excavated when the crater happened. That's a good example or a good indicator that there's a lot of ice below the surface, so that when the impactor came crashing through here and vaporized all the rock and ice, it basically threw out mud rather than dust. So we've got these rampart craters, and they're very prevalent up in this area where we would expect the ocean to have been in the past. So does that make sense that you would find buried ice underneath in the area where there used to be an ocean? It could work. Similarly, this process of patterned ground where the freezing and thawing of water in the soil over time creates these cracks that get bigger and bigger. And so this patterned ground is also thought to be a good indicator of soils that have a high concentration of ice and water that continually go through these freeze-thaw cycles that break up the ground this way. So we've got the shorelines. We can interpret those as maybe a couple of different oceans in the past. We've got features on the landscape in this area that tend to be associated with a lot of water. So, you know, it's a hypothesis worth looking at. Again, this just shows where some of this patterned ground and so forth is found. Okay. But ideally, we would like to have some independent tests of this idea. So, it's one thing to identify shorelines from orbit. How would you actually test whether those were indeed shorelines of an ancient ocean? We've talked about the MOLA data a lot. How could we use the elevation data from the MOLA instrument to test whether those, what we are calling shorelines, are actually shorelines?
See how steep the incline is?
We could see how steep the incline is. That might tell us something about how a shoreline would have interacted with the surrounding area. It's probably not the most strong use of the MOLA data. How else could we use the MOLA data to test whether these, what we're calling shorelines, are shorelines? What do we know about the shoreline around the Atlantic Ocean in terms of its elevation?
Lower than the ground. I mean, lower than like.
Yeah. Okay, but the shoreline itself, if we trace the shoreline of the Atlantic Ocean from spot to spot to spot, what do we know about the elevation of that shoreline?
Is it like the same throughout?
Yeah, where does the term sea level come from?
The shoreline?
Right. Every part of the ocean, more or less. I mean, the oceans are flat, generally speaking, right? You can't do downhill water skiing, right? So if these were actually shorelines, what would we predict about their elevation from one spot on Mars to another?
They'd be continuous or constant.
Constant elevation, which is what the MOLA instrument can provide us. So that's what was being tested in this study. We've got very precise elevation measurements for every spot on Mars. So we can plot the elevations that we see from low elevation to high elevation as against the longitude around the planet for the shoreline. So here we have 0 degrees down here. So if we look at these two shorelines at 0 degrees, what elevation are they at? Then if we go over here to 30 degrees and look at those two shorelines, if these were actually ocean shorelines, the elevation for the Arabia shoreline should be the same at 0 degrees and at 30 degrees and at 60 degrees and 90 degrees and so forth all the way around that basin. Same thing with the Deuteronilus or contact 2. And here's what we actually see in this figure down here. The bluish data are for the inner contact, that Deuteronilus contact, and the red dots are the data for the Arabia shoreline. So if you look at the red dots, are they all at the same elevation? They're all over the place. So, this elevation data tends to suggest that that Arabia shoreline is probably not a shoreline, because if it were, they would be all at the same elevation. Now, what about the inner contact, the contact 2, the Deuteronilus shorelines?
It's pretty constant except for a couple areas.
Mostly constant, but there are a couple of areas where, here we've got some areas where the shorelines are lower than we would expect them to be. And here we've got an area where, so here lower and here higher than we would expect. So does that mean that there was really some kind of funky ocean where it wasn't actually level in the past? Probably not. I mean, physics is still going to be physics. But if we look here at, say, 240 degrees, which is where this elevated measurements are at, 240 degrees is right about here. So what else here is here at 240 degrees? The Tharsis region. So it's possible that this was actually a level shoreline in the past, but as Tharsis developed, those rather than just covering over those shorelines, the Tharsis bulge pushed them up and elevated them compared to where they would have been in the past. And these shorelines that are lower than expected at 120 degrees is over here. Actually, it would be these where it loops around back here. And it's hard to say what's going on there. We don't see any real obvious tectonic factor that would have caused the whole crust to sink. But there's nothing that would necessarily rule that out over the course of 3 billion years. So from this study, it seems like there is supporting evidence for at least one of the shorelines, and maybe not for the other. Just want to quickly go through some other supporting information, and it has to do with river deltas. So deltas occur in general where you have some river system flowing out into a body of water, whether it's a lake or an ocean. And the water that's coming down through the channel is going to be carrying a lot of sediment that has been scoured out of the channel. But when that water hits the ocean, its velocity is going to slow way down, and slow water can't hold that material suspended anymore, and it just kind of forms this river delta at the edge of the ocean. So if we had another river coming in at a different point along the ocean, it would also dump material out and would form a delta, you know, again at that place where the ocean and the land are meeting. This just shows it maybe a little bit better. So here we have a schematic of how the hydrosphere might have worked on Mars based on how we know it works here on the Earth. Again, you have precipitation leading to water vapor in the air, then that evaporation leading to water vapor in the air, then that precipitation can come down as rain or snow. And if the valley networks really were ancient river systems on Mars, they would have carried sediment around and dumped that sediment to form deltas not only in the ocean but and any kind of lakes that the rivers went into. So there's now a database, given that we have much higher resolution images, of all the delta structures that have been identified on Mars. And these researchers identified 52 structures currently on Mars that look like ancient river deltas. And again, if these were deltas leading into the ocean, what would you predict about their elevation?
They were a higher elevation than the ocean was? Like they were going downstream into the ocean?
They would be going downstream, but where you would find them right at the shoreline, right? Okay. So again, if there was an ancient sea level on Mars and you had multiple deltas around this ocean basin, what would you expect to find for their elevation from one delta to the other to the other?
It would be the same.
Same thing as we were talking about with the coastline. So this is another independent test that we can make. And this just shows the elevations that I've been identified for 52 of these delta deposits. And you can see that, they are not at the same elevation. You've got some that are much higher. You've got a bunch that are kind of clustered around here, but clearly they're not all at one level across the planet. But there could be two kinds of deltas that we're identifying now. We could have deltas that were formed at the edge of an ancient ocean, and then we would have deltas potentially also that would be formed in lakes that would have been also present if Mars had a hydrological cycle. So the researchers differentiated between those deltas that are going into a closed basin, which is what you'd expect with a lake, versus deltas that are going out into an area that cannot be, identified as a closed lake basin. With the idea that would be that these open ones represent ocean deltas, and the closed ones would be lakes. And we know the lakes are going to be higher elevation than the ocean. So if you make that distinction, you can see that the lake deltas are indeed all over the place at different elevations, but the ocean deltas really are at a fairly constant level across this diagram. This just shows that in more detail. And these ocean deltas are at a level that's about 2.5 kilometers below the mean the mean elevation that's been defined on Mars, since Mars doesn't have a sea level anymore. If you look at that, that would have been an ocean that would have looked something like this. If you calculate the volume on that, it's not quite the volume that we have in terms of the oceans on the Earth, but it's still a fairly significant body of water, which is what's being supported by more and more evidence as it gets collected. So I think I've got a couple of extra slides here, but I don't think I'll bother with them. Take-home message is, take-home message. For a long time, people kind of poo-pooed the idea that Mars ever had an ocean, but we now have these multiple lines of evidence that all seem to be reinforcing each other to indicate that it's likely that Mars had some kind of ocean structure early in its history.